And the way it came in 2016 was talking about there was a question which came, was talking about the processes that chemicals undergo. The processes that chemicals undergo, we were saying that these are chemicals as they undergo some transformational processes. At the end of the day, they may be more harmful or less harmful, depending on one, the nature of the process that the chemicals undergo, two, what happens to the chemical structure. Yeah, so we're saying that when a chemical undergoes certain transition, it is either the chemical at the end of the day gets to be more dangerous than it really was at the beginning, or it will be less harmful as it was at the beginning. That's what this lesson 5 it talks about under exposure assessment. And then we're saying that these chemical transformations may be categorized in two ways. There are those that are spearheaded by microbes or by living organisms. Those we call them biotic processes. And there are those that do happen by chemical means that we call abiotic processes. So there are biotic processes as well as abiotic processes. Okay, now, so it's important we understand that the abiotic transformation we're talking about the chemical transformation, the chemical processes that the pollutants undergo. And among them, there are 4 important processes, because in that question, it was really requiring us to indicate the biotic processes as well as the abiotic processes. And among the abiotic processes that we are really going to look at are these 4. Number 1, there is what we call hydrolysis, the first process. Then the second one is oxidation. The third one is reduction, and the fourth one is photochemical transformation. So these are the 4 processes that we need to talk about if we are to handle that question in the way it came. Then under each process, under each process, there are examples of chemicals that we can pick out. Under hydrolysis, there are certain compounds that can undergo hydrolysis. They are also under oxidation, the examples that we can talk about, the reduction as well as the photochemical processes. Except that this one is a little bit tricky because it talks about real organic compounds. Just a minute. Okay, so yeah, that's what I was saying. And on the same part, there are definitions that we're going to understand. What is hydrolysis? What is oxidation? What is reduction? What is photochemical processes? So 1, we need to give the definition of these processes. 2, we need to give specific examples of compounds that undergo these processes. Then 3, we need to state what happens to the chemical after it undergoes any of these processes. does the chemical becomes more dangerous or does it become less harmful? Because that is the many components that we are dealing with today. Okay, so let's go now and look at these processes. So, by the way, let's look at some of this information they provided us. They're saying following the release and the transport of chemicals into the environment, that toxicant may undergo various biotic as well as those that we call abiotic processes. So it might undergo any of the two. And when that is happening, what is happening is that its chemical structure is being modified. It's being changed. And if the compound gets to have its structure changed, you find that even its effect on the human being may be changed. How do I bring this to a real home situation? We look at a toothbrush. I don't know if a toothbrush. Okay, what is it called? I don't know. Toothbrush, whatever it is. When we get to have its structure changed, you find that even its duty that it does may be affected. Look at a cooking stick. When you change the last part of the cooking stick, even its work changes. So the chemical modification of the structure may result in the effect of that compound changing. Now, those ones whose concentration likely to reduce, that in itself we might refer to the point we call degradation. Yeah, so we're saying the transformation degradation is a disappearance of the parent compound from the environment by a change in its chemical structure and in its toxicological properties. Something that I said that when a compound gets to have its structure change, you find that the real one, the actual compound that it was at the beginning, and the one that we get to have at the end of the day will be different. Why? Because its structure will change. And when the structure changes, even the properties to do with how toxic that compound is may change. Yeah, let's look at salt. When we get to have that salt, maybe soap, which is a solid, and then when we leave it in water, it dissolves in water. At the end of the day, the properties of that salt, which the soap will change. If it was rigid, you find that at the end of the day, it becomes very slippery and eventually it dissolves. Its chemical structure will have contributed to that. So we are saying that these transformation processes have got two effects. One, it is either at the end of the day that compound becomes more metabolite toxic, or it becomes less after undergoing those transitions. For as long as that compound has undergone those processes, any of those, the structure will change, and these are some of the results. If the way it was from the beginning, that's the way it gets to be, even at the very end, just know that that compound did not undergo any of those processes. It is just the way it was. It did not react with water. Because if a compound undergoes, I'm just trying to check for the battery percentage. Sorry. No, it's draining. I think it's got issues. Okay. So that's what we are trying to say. For as long as that compound has undergone hydrolysis, undergone oxidation, reduction, and photochemical, the concentration or the structure can never be the same. Okay, so now let's understand these transformational processes. There's some few things that I may remove and some things that I may add. When they say polar transformation products, the polar compounds, these may be hard to understand from the geometry of compounds. So some of these things I'll be leaving them out. Okay, now we are saying that how fast the happening of the transformational process, how fast this happens depends on the following. Remember, when you leave a plastic outside. When you get to two plastics from ShopRite, one plastic is buried in the soil, then the other one is left where it's just left on the sun, then the other one is inside of the house. The way these plastics will be, okay, let me not talk about the plastic, let me talk about the cloth. One cloth in the house, the other one out, or maybe on top of the roof, then the other one the soil. These three places will have different rates at which those clothes will be disintegrating or be degrading. So the degradation of these chemicals, what do they depend on? One, the availability of the reaction. We may have one compound that may undergo a series of reactions. The same compound undergoes hydrolysis. The product of hydrolysis also undergoes oxidation also. So the availability of reactions may determine how fast this compound degrades. The other one, the intrinsic reactivity of a chemical species. Okay, let me just check where I wrote this part. The intrinsic. The intrinsic reactivity. Okay, so the intrinsic of reactivity means okay, I think I'll find that later where I wrote it. Then I'll come and explain later. Because I felt it's important to understand when you say intrinsic reactivity of a chemical. Okay, maybe just because when you say intrinsically motivated human beings, these are the human beings that can work on their own without supervision. An intrinsically motivated personnel is the one who's able to work without being pushed. So when you say intrinsic reactivity of a chemical, we're talking about the ability of that chemical itself to react without in the absence of certain factors. How do I put it? There are certain compounds, let's say sodium hydroxide. Sodium hydroxide, when you just put it on the surface, even in the absence of water, that sodium hydroxide is able to react with air and it melts. That is the inability or the inside ability of that compound to react minus it being pushed. You know, there are certain reactions that are very slow for the reactions to take place unless you apply a little bit of heat, unless you do a little bit of stirring. Now, the inside ability of these compounds to react on their own. That's the point over there. Then at times, these compounds may be very much available to react, like hydrolysis. The hydrolysis is the reaction of a compound with water, but if there isn't enough water, you find that this compound cannot react. That's why we are saying that the other factor that affects how fast the degradation of a compound is taking place is the availability of things to react with. Yes, that's what this point is trying to emphasize. Then the last one says, it's even cut. The reactivity of a reactant depends on the environmental condition. Yeah, it's very true. Now, this is just a backup of this point here. They are saying there are certain compounds that are able to react without even being pushed, without even having their conditions changed. On their own, they are able to react. But again, we're saying that how fast that reaction goes depends on certain thermodynamics properties, such as temperature, pressure, as well as the volume of these reacting species. So that's what the point is talking about. Now, this part is very important because there is a point ahead of us where they talked about pseudo rate. I don't know, maybe let me just get to that. Okay, so, yeah, so they were just talking about, just trying to bring now the highlights of what is hydrolysis. Hydrolysis is a reaction of a compound with water. At the end of the day, it gets to have its chemical structure are changed. I talked about salt, which is powdered. If you want, you can even get powder. You can even get that. You can even pinch that salt with the hands. Just push two hands together, and you can get to have salt. But when this salt dissolves in water, it becomes difficult for you to do that. So because its chemical structure will have changed. Then the other one, which is oxidation. I was saying oxidation is defined in two ways, three actually. But of those three ways in which oxidation is defined, they just picked one. And that one is the transfer of electrons. But what does it mean? If a compound has lost electrons, it means it has been oxidized. But for the compound to lose the electrons, there must be someone to receive. When I go to the booth to send the money, the agent asks me, where do you want to send the money? At me, I just want to send. They'll start doubting the normality. Why? Because for as long as I'm sending, there must be a human being to receive. That's what this point is telling us. But when a chemical species loses electrons, it becomes oxidized, and that substance which has gained electrons, is said to have been reduced. So the reduction is a receiving of electrons. Now, I want to put a very critical statement here. If there is no one who wants the money, no one will send. If I don't ask for money from the big boss, Mr. Levias, you are not going to send. So why am I saying that? If you send me money, I am the one who caused you to send. So this point says oxidation is a losing of electrons. And the reason as to why that substance lost electrons, because there is a person who wanted electrons, so he's the one who has been pushing that chemical species to let go of electrons. As a result, that which receives electrons is called an oxidant. An oxidant is a substance which receives electrons, and that substance is said to have undergone the reduction process. I don't know if you have gotten that, Mr. Regis.
Yeah, it makes sense.
Okay. Then the other one is a photochemical. Now, when you hear of the word photo, the photons, we are talking about light. Yeah. So when they're saying photochemical degradation is a transformation of a chemical substance due to the interaction with sunlight. Something that we see even in nature. You get to have this car has been parked by the outside garage for years and years and years. What happens to the paint? Starts fading. It's because of the photo interaction of that paint as well as the sunlight. So these are some of the abiotic, or you can also call them chemical processes that alters or that change the chemical structure of compounds. Then biotic, we are saying biotic, these are processes, the biological processes, and then they are also called because they are brought about by very, very tiny organisms, which we call microorganisms. In general, the ones that are used are microbes, which is a combination of the bacteria, the viruses, as well as the fungi, the microbes. These are the ones that play a very, very important role in the breaking down of compounds, chemicals. Okay, so let's see how far we can go now. Okay, but maybe before I get to that, I need to give a real situation. Just allow me to check the battery again. This thing has got issues. You might think it's charging. Gosh, it's draining. Now it has been on 57 for quite some time. Okay, so there's an important concept that we're going to look at. This one is very, very important in the inorganic world. At times, even in the analytical chemistry, you may talk about this a little bit, but it's highly talked about in the inorganic world. There's a concept we call rate of a chemical reaction. And these rates of chemical reactions, they point us back to what happens in nature. If you have a garden at the backside of the yard, that garden, you've got vegetables. Then you realize that the lot of organisms that are eating up the leaves. What do? You run to the nearest agro shop, you buy the insecticide, you spray on the leaves. When you spray on the leaves, there are two parameters that are very, very important. Parameter number one, we can talk about parameter number one, we can talk about temperature. No, not with temperature. We can talk about concentration. That's the first thing that we're going to talk about. Why concentration? Because we have applied concentrated chemicals on the leaves. So the first one is concentration. Then the second one that we're going to talk about is time. Why are these two important parameters? It is because when those chemicals are on the leaves, then the agro agent will indicate to you that, please, you can only pluck these leaves from the garden after a week. Why? Because there is a time involved in there. So if the time is in days, well and good. They'll say after 1 week, time is a factor. Why? The other thing is concentration. Why are we saying concentration is very important? Is because as time goes by, the concentration of that medicine we'd sprayed on the leaves, as time goes by, the concentration will be reducing. So that transition itself, what is it that is happening? We are getting to have the metabolite toxicity becoming less at the end of the day, because we had sprayed on the leaves, and then those leaves, what did they do? They got the concentrated drugs within themselves, and then when the amount of time indicated is reached, we are going to pluck those leaves because the concentration will have reduced. Now, why are we saying this? The reason is this. There is this point which is talked about, is a little bit of calculus, but I wanted to bring it out in that way so that we understand. The catalyzed by hydrogen hydroxide ion, just concentrate on this part here. When they say dC over dt, that is the point I was trying to emphasize on. From the other end, because we have not really done much of calculus, so certainly derivation may be a little bit difficult. Even this other experimentally equation, when they say in, that is lean, the opposite of logarithmic, but we haven't done logarithm function, so some of these things I'm not going to talk about it. Yeah, so what I'm saying is that the dC Okay, just a minute. Just a minute. So tomorrow. Zero. But these are not needed. I just want you to go slowly. Yeah. Sorry about that. Yeah, so I was saying, the way they drive these things, first you need to have a background of mathematics. That's why I'm trying to take a different route to explain, then I come back to this. So this in itself is telling us that the change in concentration as it undergoes the hydrolysis process, it is a function of time, because the change in concentration has to be with respect to time. That's what this point here is trying to say. So in that question, one thing we can say about hydrolysis is that what is produced at the end of the day is metabolite less toxic, because that's what the point is trying to say here, that the concentration of the chemical as it undergoes hydrolysis, the concentration reduces, it being a function of time. And the way that the process takes place is by the rate of a chemical reaction we call pseudo. And these are some of the things that we may not understand, because unless you had done in organic, there's pseudo, first rate, there's first order, the second order, the third order, and then the pseudo. So these are some of the things, but we may not have much information about it. But the only thing that we can know is that as a pollutant undergoes hydrolysis, we'll get to have its concentration reducing with its time. And at the end of the day, the product that we're going to form is going to be metabolite less toxicant. But provided that that substance is soluble in water, because if it is insoluble, we will reach a point now from the biotic, which is a bioaccumulation and the biomagnification and all that. But provided this compound has to be soluble in water. Ba boss, ndinde butuka sana. Okay. Now, the challenge that we might have here is understanding now these chemical compounds. But allow me to just, there's certain things that in life if you can't really understand it better, we memorize. So remember I said under each process, there is a specific example of a compound that we can look at. So under abiotic transformation and the process is a hydrolysis, the compound that undergoes the hydrolysis is an ester. So an ester is the first example that we've looked at, which undergoes esterification. Oh, sorry, not esterification, the method of producing esters, but hydrolysis is the opposite of esterification, where we get to have the ester being broken down into two important compounds, which we call the carboxylic acids as well as the alcohols. So this is the alcohol, and this is this is the carboxylic acid, and this is the alcohol. But maybe just to borrow some information from the chemical world, we can do what we call a structural demonstration of how the hydrolysis takes place. So to start with, I don't know if this will be necessary, but it's just important to demonstrate. So when you say an ester, there's something that must be present in that compound. There must be carbon, and then there must be a double bond to oxygen. There must be a single bond to oxygen again, and then there must be a single bond to another carbon. The chain continues. But we are reacting with water, so water has to be written like that. Okay, then there's oxygen here, and there's hydrogen here. But when you look at the way this process takes place, there's a little bit of heat. At times you may have heat, at times you may have an acid. Now, these are some of the organic reactions that we go in detail learning. Now, how that happens is that we have that, and we have that. Okay, so that in itself will be this O C will be attached, or the hydrogen will be attached to that. And at the end of the day, we already have this part. We already have this part. C, we have a double bond to O. Now there's this free bond. This free bond, that is where this bond will be joined. And at the end of the day, we're going to have this. So this is the formation of the carboxylic acid. Then there's this carbon here. We're going to have carbon here. There's this oxygen. We are going to put a single bond oxygen. Now, after oxygen, there's this bond which was being shared. That's where the hydrogen will be attached. So we're going to have H, and this is the alcohol. So that is the hydrolysis of how an ester is broken down into a carboxylic acid as well as an alcohol. But this is just for the sake of demonstration. In toxicology, you don't really show this. Just indicate that the reactant or the pollutant or the compound that may undergo an abiotic transformation by the method of hydrolysis, the example we can look at is an ester. And the products that are formed are less metabolite pollutant. The example of an ester, the butyl acetate, so it's just an important component here. If you want to be more specific, just tell them even the products that are formed. That is one. Then number two, I think yes, you can, there's some of the things that you need to understand. Now, what are esters? These are just flavors that we use in food. These are the flavors that we use in spray. These are flavors that we use in roll-on. These are esters. The other compound that undergoes hydrolysis is an amide to produce the carboxylic acid as well as an amine. So when an ester is breaking down, always we need to know that the carboxylic acid is formed. And when an amide is breaking down, we need to know that the carboxylic acid is found. So we have a common product, the carboxylic acid. But what determines the other compound to be formed besides the carboxylic acid is this part, which is here. Look here, we've got nitrogen and the chain. There we had oxygen and the chain. So because of the presence of this nitrogen, it will bring us, instead of producing an alcohol, we're going to produce an amide. So two compounds that undergo hydrolysis, an amide to form carboxylic acid and an amine. We also have an ester rather, to form a carboxylic acid as well as an alcohol. These are other examples of compounds that undergo hydrolysis. We may not even look at them. The carbonates to form the amides plus the alcohols and the carbs. These are some of the things that. So those two are very easy to remember. Okay, but we are saying among these organic compounds, some of them are very much innate. Some of them cannot react with water. So if these compounds are in our bodies, we understand very well that inside of our bodies there's water. So if these compounds cannot react with the water in our bodies, what happens is that these compounds will be getting accumulated in the body, resulting to what we call bioaccumulation. It now brings us to the future that we're going to look at a later stage. So we're saying some of these compounds that are pollutant may be very, very much innate. They may not react with the water. But again here, I bet to disagree among the compounds that have been listed here. We have these guys just from being talked about that esters do undergo hydrolysis. So why on earth did they put them there? So this is wrong, because esters do undergo hydrolysis process. Perhaps we may talk about alcohols, the ketones, and then the polycyclic aromatic compounds and Pcbs. Remember the Pcbs? The other day, I don't know if you were there, Mr. Revius, we're looking at the properties of the Pcbs, and the properties that we looked at. The major ones is that this compound is insoluble. So if it is insoluble in water, in the presence of water, other compounds are undergoing hydrolysis, forming products that are metabolite, less toxic. These Pcbs will just be piling up in the bodies. As a result, it results to what we call bioaccumulation. Okay, so that is all about hydrolysis. The other one is oxidation, and we are saying oxidation is the losing of electrons. When an element loses electrons, it is going to lose electrons because there must be a chemical compound that is ready to receive. And that which receives is called an oxidant. Now, what are some of the compounds that are able to gain electrons? The ones that we call oxidant, these are the ones. Number one is what we call alkyl radicals. An alkyl radical just brings us back to what we just from talking about. R represents a chain. In organic chemistry, R represents a very long chain of carbon and hydrogen. Then from a very long chain here, we've got oxygen, and oxygen by nature is supposed to have 2 electrons that are bonded, but we have one that is used in forming this bond, and there is a free one here. That's why they have indicated that as a radical. So when an electron is being donated to this, we are going to have this electron disappearing. So radicals are very, very much reactive chemical species. The other one is what we call the peroxil radicals. The peroxil radical just comes back from what we discussed. We have R, a very, very long chain of carbon and hydrogen, and then we have a double bond to oxygen. We have a single bond to oxygen, and remember for esters, we put R, but this part is not there. When we put hydrogen, it becomes a carboxylic acid, but all these things are not there. So because of that, that's why we are putting that, to show that this thing can react. That is a peroxyl radical. Then the hydroxyl, remember what I just demonstrated, that when this water here is undergoing hydrolysis, what's happening to this water? We will have one of the bonds breaking, and the bond that breaks is this bond here. So when this happens, we're going to have this free electron that was used in bonding is ready to attack. So that is the one that is there. So these are some of the compounds that are able to support the oxidation of the chemical species. Now, remember we said one of the factors that determine how fast the compound is going to degrade is the availability of the reactant. So if you have a situation whereby there is a chemical pollutant which is likely to lose electrons, how fast it's going to lose electrons will depend on the availability of this, because these are the guys that are going to accept the electrons towards themselves, and that's why they are called oxidant. And they're saying most oxidants are formed from a chemical that interacts with solar radiation, forming an excited state of the molecule. So these molecules that we're seeing here, very much excited, very much ready to attack. Now, saying from solar radiation, the other point that I may bring to your attention is the formation of CFC, chlorofluorocarbons, CFCs. Those that are used in the depreciation of an ozone layer, the CFCs, which are some of the pollutants. I'm sure maybe we're even going to find them. The CFCs, these are compounds that are produced from CFCs are pollutants that are produced from these ones here. These are classes where we produce the CFCs, these pollutants. And how the reaction takes place, resulting in the production. It is even here. How did I pass? The CFCs, the chlorofluorocarbon. These are the ones that are produced in the air conditioners, the aerosols, as well as the refrigerators, the ones that are not working. They produce the CFCs on a very large scale. And these are the ones which are bringing even global warming, because they go in the atmosphere to go and react with the ozone layer, and at the end of the day, the ozone layer reduces its thickness. So the absorption of radiations from the sun reduces. As a result, we are receiving direct harmful radiations from the sun because the CFCs are being depreciated. Now, why am I saying that? I was just trying to connect to this point where I was saying, where were we? No, let's go outside. Where I was just talking about it was ahead, okay. Where I was talking about the solar radiation, I was saying, instead of the CFCs being produced from the refrigerator, we can also have the CFCs being produced from the alkanes in the presence of the solar radiations. The solar radiations is there to help in the formation of some of the radicals which are not here. We call them the chlorine radicals, Cl radical. When this Cl radical is produced, is very, very reactive. It is able to react with an alkane in the substitution reaction to form the CFCs. That is the point I was trying to bring out. Why we are saying that the solar radiations are very, very important in the production of these radicals. Yeah, so it even brings me now back to the CFCs. The half-lives, we don't need to go that way. The half-lives, that is a little bit talked about in nuclear chemistry, but these are just some of the things that they bring on board to support the thesis of CFCs. So we may not go into half-lives, but it's important that we understand the CFCs, that are the ones that are produced in the refrigerators, in the aerosols, in the air conditioners. At times they are produced organically, and their threats is on the ozone layer. But boss, if you have something to ask before I talk alone up to the end.
Oh, what I do is, I note down. If I tend to disagree or I should clear pamu after nakabirenga kuna put nara the pusher.
Okay.
At times where you teach, and then preparing an extra question. I don't.
Oh, okay.
Do we discuss and then potentially clear on the.
Okay. So that is then the example of a compound that is likely to undergo oxidation. I was even telling Madam Shatu to say, I will do not allow you to develop headache in the mastering of some of these compounds, because some of them, they require you to have a bit of organic knowledge. The P here, what does it stand for? You see, this stands for para, the position of this thing here. P chloro, the position is called para. I saw some guys who did chemistry, they were trying to dramatize the new name for Facebook, Meta. Meta, we use it in chemistry to represent the position of a substitute at, if this is carbon 1, carbon 2, carbon 3, carbon 4, 1,4 is called para. Then 1,2 is called meta. So some of these things you may not even understand them later. You need a little bit of introduction to organic chemistry, in particular the aromatic chemistry. So I said, I'll look for basic compounds that will be able to remember, the ones that undergo oxidation, the one that you can easily remember. But of course, among the ones that we've mentioned, the one that undergoes oxidation is an alcohol. An alcohol is able to undergo oxidation, and at the end of the day, we produce a carboxylic acid. I may talk about this, I may not talk about it, but if I feel that the alcohol as a compound that undergoes oxidation is important for us to use, then I will have to come and demonstrate how that is done. Because oxidation, at times, now these guys are very stupid, allow them to go that way. Because they say from there, remember I said oxidation can be defined in 3 ways. One of the ways is the losing of electrons. The other one, the other 2, though the other 3, I didn't talk about them. But one of which is an addition of oxygen to a chemical compound. Look at this compound, it does not have oxygen within itself, but one has been added. So because oxygen has been added to this compound, we are gonna call it oxidation. Now you see, these are some of the confusing stuff that I was talking about the other day. They just make mention of one way in which the oxidation. Anyway, this is masters, know that you are likely to research. So oxidation may be defined in terms of gaining electrons, may be defined in the addition of oxygen to a chemical substance, may be defined as the losing of hydrogen. It is all called oxidation. So you can talk about how many hydrogen atoms are in here. We've got 2, we have 10, we have 2, about 14. But when you check how many are here, we've got 2, we've got 8, we have 9. So hydrogen has been lost. It is 2 points back to the oxidation. Oxidation may be defined as losing of electrons, losing of hydrogen, or addition of oxygen towards itself. So even here, I may look at the simple compounds that we can use to illustrate the oxidation process. And then the opposite of oxidation is what we call reduction. The opposite of oxidation is what we call reduction. So if you are saying the oxidation is the losing of electrons, this one has to be the gaining of electrons. For an example of a reductive transformation, electron transfer from ferrous 2+ to 1,2 dihalogen substituted ethane. Okay, so let me try to shed more light on this part. Eth means 2 carbon atoms, so you may have 1, 2. If you allow me to number these carbon atoms, I might have carbon 1, I might have carbon 2. But they're saying 1,2, meaning on each carbon atom, di means 2. Dihalogen, a halogen could be chlorine. So on each carbon, I might have chlorine here. Even here, I might have chlorine in trans or cis. So this is the compound they're talking about, 1,2 dihalo substituted ethane. So all in all, they are saying we can have electrons being transferred from this compound to that. So the moment this compound gains electrons, it means it has been reduced. Among the compounds, they focus much on organic compounds, the nitro aromatics. The nitro, nitrito, these are some of, that's why I said I might look for beta examples. Because when I say a nitro aromatic compound, when I say a nitrito, halogenated aliphatic, aromatic, these are some of the organic compounds that may be very dioxin. These are some of the homologous series that you might have learned a long time ago, or maybe that you need to understand. Because the question becomes better if you understand the question, you can even bring in your own information. But if they use a compound, the aromatic aliphatic, aromatic, it changes everything because you don't really know what the compound is all about. So we have to look at the simpler examples that do undergo reduction. Same applies to this. Dehalogenated, the hexachlorobenzene. These are some of the things that I need to look at within me. So that I come up with examples that will be very easy to remember. Then this process depends on the environmental factors such as the pH. In other terms, the pH may influence a compound, resulting it into losing electrons. Yeah. The redox potential. This comes now from the electrochemistry. Again, it may be hard for you to understand. So better go for pH, which is common, the temperature, as well as the physical chemical characteristics of the pollutant. The characteristic of the pollutant itself will determine how fast it reacts. Remember, we looked at the intrinsic reactivity of a chemical compound. It points back to its characteristics that it has. Okay, so that is where so these are some of the things that undergo reduction. Yeah, that's it. I'll look at examples that are very common. Then look at the photo degradation. Photo, remember we're saying light is involved. And the things that will depend or that will determine how fast the reaction takes place are the ones that are listed below. One, there's light intensity. How much light is present will determine how fast the reaction takes place. Like I was talking about 2, 3 pieces of cloth. One is inside, the other one is buried, then the other one is exposed to the sun. How fast these guys degrade depends on the light intensity. Yeah, and the second one is the one that's listed right over there, the extinction coefficient of a compound. Now, when you say the extinction coefficient of a compound, there are 3 things that are involved in there. Might even be narrowed down 4. One, there are some clothes. Let's say, let me talk about asbestos. Asbestos are able to absorb light, allows light to pass through it, but not at a very greater extent as compared to the iron sheets. Then, when light is allowed to pass through, like some compounds may allow light to pass through, but there is also need for light to be absorbed by the compounds. Light may just pass through, but are the compounds able to absorb light? Let me not talk about light, heat. When you are boiling 2 items, cooking oil as well as water, believe you me, you find that water does not contain as much heat as cooking oil can be. Cooking oil catches a lot of heat. That's the reason as to why frying, we don't use water. Because water will take a lot of time to do the job because it doesn't absorb a lot of heat. Okay, let me give 3 examples. One, you get the raw meat, you put on the sun. The other raw meat, you put in the water, the heating water, then the other raw meat you put in cooking oil. Believe you me, the one in cooking oil will be fried fast because it catches a lot of heat. May allow light to pass through it, but the ability of it to absorb heat in terms of photons is at a very, very great extent. So as a result, if a compound is able to absorb more heat, it's able to degrade very fast. That falls under extinction coefficient of a compound. Then the other one is that even if this compound allows the heat to pass through it, gets to have the heat transmitted, is it able to allow the heat energy to go to the reactive site? Remember what I just looked at. I looked at this guy here, the alkoxyl. And then I said, this free electron, the radical, is very, very reactive. So you might have heat energy on, or maybe you might have, remember this is a reactive site. So I'm just giving an example. If this compound gets to have heat on every part of a long chain without heat reaching the reactive site, you find that this compound will not degrade. As a result, when someone gets to partake of this compound, which still has a very active site, you find that it may have problems. Believe you me, in the advancement of science, it is advisable that when cooking, although this is not common, but in the actual sense, organically, when cooking oil is used to fry vitumbua, to fry meat, to fry whatever we are frying, that cooking oil forms what we call epoxides. And those epoxides, they look like this, an epoxide. Cool, the chain continues, and there are these bonds. Now, what happens is that when you cooking oil, when you use cooking oil, these epoxides are formed. And when these epoxides, cooking oil, cools down, you come to reheat it, you find that this bond breaks. And when an epoxide will have the bond broken, these two electrons that were used in bonding will be set free. As a result, what happens to these electrons when you eat them? They're so deadly. That's the reason as to why they do not advise to take hot tea using a plastic cup, because those plastic cups are made by the process we call polymerization. And during the polymerization, certain electrons are quenched. An electron is just put to sleep. But now when you apply hot tea in there, you're activating that electron, and the partaking of it may cause some side effects. So that's saying the reactive site is very, very important in a chemical structure. So remember, when we're talking about the degradation of a compound, we're talking about what happens to the reactive site. If the compound gets to have the reactive site, heat transmitted on that site, and then the structure is changed, at the end of the day, that compound will be metabolite less toxicant. Then the other one talks about the chemical reaction, which is very common. Yeah, so these are the three things that, these are the things that are very important. Then among the things that do where the photo degradation depend on the photochemical transformational process is the aquatic environment. The influence of dissolve of particular matter on light intensity. Okay, these ones are not very important. These ones are not very important. Okay, so again here these guys are not very good. The examples are using just organic, polycyclic aromatic hydrocarbon. The polycyclic, that is where the Pcb falls. We have the cyclic aromatic hydrocarbons, which are benzene. Two of them, they are interjoined. That's why I call the poly. We may have one, you may have two. The phenolphthalein, the indicator that we use in the lab, that is one of the examples of polycyclic aromatic hydrocarbons. So what are they saying about them? They're saying that they tend to be highly susceptible to photolysis due to their high capacity to absorb sunlight. These guys absorb a little bit of sunlight. Remember, that's what we said. Is it having the ability to absorb sunlight, among others? Okay, some of these things, hydrolite, these ones will come and I'm not just comfortable the way they are using some of the words for people who have not really done organic. It becomes a little bit hard. One, you start understanding these compounds, then later on, you understand the concept. So yeah, when answering that question, I'll make sure that I use examples that are very easy to remember. It's just a summary of the photo. Now this one is photo oxidation and the hydrolysis, precipitation. They're just showing me how this compound, which is the parathion, this compound can undergo multiple processes. It undergoes photo-oxidation, the oxidation that is spearheaded by light. And this compound, you have its form transformed in this way. Okay. And then, is it having anything changed? Okay, there's a phosphate here, C250. Oh, see, it's just the same. I wonder why the name has even changed, but it's just the same compound. It's para also, 1 by 4. There's a nitrate here, the phosphate. Oh no, there's a change in terms of the compound. Look here. It's called oxidation because oxygen has been added to it. Same compound has undergone photo-oxidation, having oxygen added to the chemical. Instead of sulfur, I've got oxygen here. And then the same thing undergoes hydrolysis, where we get to have this part sliced out. Dang, we have OH. And then this one also will get to have its structure drawn like that. So we may have the same compound that undergoes more than one abiotic chemical structures. That's what this point was talking about. Those are organic compounds. Okay, so that is where the abiotic transformation ended. You can go back and look at them. One, there's hydrolysis, where we talked about amides being converted to amines and the carboxylic acids. We also had the esters that were being converted from the esters to carboxylic acids and alcohols. And then the other process was the oxidation, where the examples, I might give you simple ones, not really organic in nature, but I might give you inorganic because inorganic compounds are very easy to remember. The other one was a reduction, and then the last one was a photochemical transformation or photo degradation. So those are the four important processes that we can talk about. Okay, so do we need to switch even to the biotic, or maybe we can do this tomorrow? Hello? Boss? I'm quiet.
Yeah, and we can do it tomorrow if you don't mind, so that whatever at least the time here
Okay, okay. Yeah, so Peter, more as you go through, as you Peter more, you have challenges. I'm saying, okay, just find time to go through. I'm also going to send you the recording. Then if there are challenges you are going to be faced with that, then you can just let me know so that I find, or not this one, I find a way to address that.
Okay, no problem.
Okay, boss. Now, totally son.
Okay, Jesus.